US Physics Olympiad, year 2017, F equal MA, first round. On this competition for 25 problems, it was given 75 minutes. Please subscribe for this channel to get more interesting problems. Problem 1. A motorcycle rides on the vertical walls around the perimeter of a large circular room. The friction coefficient between the motorcycle tires and the walls is μ. How does the minimum μ needed to prevent the motorcycle from slipping downwards change with the motorcycle's speed v? Solution for problem 1. When a motorcycle travels by a circular motion, he experienced a normal force equal centripetal force, which is mv square over r, where r is a radius, and the force of friction will be μ multiplied by normal force, which is μ mv square over r. And to hold a motorcycle to slipping down, we need to equalize his weight mg to this friction force. So we have force of friction equal mg. And from here we can write that mg equal μ mv square over r. And from here we can find what is minimum μ. We have μ equal gr over v square. It means that μ back proportional to v square. That's the answer D, correct one. That was solution for problem number 1. Problem number 2. A mass small m hangs from a massless spring connected to the roof of a box of mass big M. When the box is held stationary, the mass spring system oscillates vertically with the angular frequency omega. If the box is dropped, falls freely under gravity, how will the angular frequency change? Solution for problem 2. If we have a system with a small mass oscillating on a spring, we have omega equal square root from k over m. But in case when this box starts free fall, we have other system of oscillating two masses connected to this spring. It means that they are oscillating around the common center of mass, and this center of mass splits this spring by two parts. Each part has coefficient of spring greater than original coefficient, and because these two masses they oscillate connected to this center of mass, it means that omega will increase because coefficient will increase. And this is the answer B. This is solution for problem 2. Problem number 3. A ball of radius r and mass small m is magically put inside a thin shell of the same mass and radius 2r. The system is at rest on a horizontal frictionless surface initially. When the ball is again magically released inside the shell, it sloshes around in the shell and eventually stops at the bottom of the shell. How far does the shell move from its initial contact point with the surface? Solution for problem number 3. Here we just need to use equation for center of mass, because initial position of center of mass will not move, and we have this equation. If we count position of this balls compared to the center of big shell, we have m multiplied by negative r, which is position of center of mass of this small ball, plus m multiplied by 0, that's the position for big shell, divided by 2 masses, that will be position of center of mass, that's equal final position of both, which is x multiplied by 2 masses over 2 masses. It means that x is equal to negative r over 2. So it means that big shell moves to the distance r over 2 to the left. And this is the answer for question 3. The answer is B.